Assalamualaikum everyone. In today's lecture we are going to cover these four topics. First one is basically effect of self weight due to the weight. Normally when we study the beams, then we neglect this effect, but today we are going to find out the deflection of the beam due to the weight. If the weight of the beam, the length of the beam is small, then we can neglect this effect, but if the length is too large, then obviously due to the weight of the beam will experience some deflection. And then we will study how we can apply the triangular load on the beam. Okay, first of all, I would cover this one. Okay, how to apply the triangular load on beam. For this one, I have an example from Hibbeler 9th edition. This is 12-22, and this is a 9 feet beam, and there's a you see that there's a triangular load here, 3 kilopounds square inch per feet, kilopounds per feet, and this is the 9 feet. Normally we have the triangular load in that form. Even if the beam is 3D or 2D, then we will also cover how we will cover that one. Okay, for that, right now the cross section of the beam is W14 by 30. This is the beam dimensions. You can get the dimensions of the beam at the end of this book, okay, in the appendix. But for easiest, I have written the dimensions here. I have extract that picture and then the dimensions from here. So you can study that our beam is W14 by 30, and these are the different parameters. Okay, using the design modeler, okay, you can first you can go to the cross section and select the I-beam cross section there, and then draw this like extrude, apply this extrude command. I will leave it to you that I hope you can draw that. Okay, just don't forget to apply the chamfer here. Okay, so I have already drawn this geometry, so I will just show it to you. Okay, as you can see here, I have just drawn the cross section from there. Okay, for that you just go to the you can just go to the concept, and there is an option of cross section, and then you can select the cross section here, and then here you can substitute the values. Okay, these values, okay, W14 by 30, which I have already done. Okay, by substituting these values, okay, you can see there W1 I have written these values here, and then okay, I have extrude that. Okay, I section beam up to the 108 inch, which is basically the 9 feet. And then okay, after applying the extrusion, I have also applied the chamfer of 0.3 inch on all the edges. You see that internal edges 1, 2, 3, 4. Okay, so the at the 4 edges I have applied the chamfer. Okay, just to avoid the stress concentration in that area. So I will just close that. Okay, I have independently drawn the geometry, so I can also duplicate that, and I can use this geometry in any type of analysis, and I can save it, and I can use it for further analysis as well. That's why I have drawn an independent geometry. Okay, so to solve that, okay, first let me show you how we can do that. Okay, just go to the static structural analysis and just drag it and put it on the geometry. Okay, just drag it here. Okay, so the ANSYS will automatically, okay, connect this geometry to here. Okay, right now you see that the elastic modulus is basically 29 into 10 is to power 3 KSI. Okay, so just let me show that, okay, what value I have here, kilopounds per square inch. So this is my steel, and here the values in Pascal. Okay, let me change it to the pounds per square inch, and this is 2.901 into 10 is to power 7. Okay, while here it's okay, kilo is 10 is to power c, so 2.9 into 10 is to power 3 kilo pound square inch. So for that, okay, I can change it to 29, 1, 2, 3, and these are 10 is to power 3, and then 3 zeros more. Okay, so 2.9 into 10 is to power 7, which is equivalent to this one. Okay, so this is I have done, that's fine. So I can close this tab, and then next is I need to open the mechanical. Okay, this is our beam, and ANSYS mechanical. Okay, first of all, just let me check on, this is my geometry. Okay, and then this is a solid model, and the assigned material is structural steel, and here we can find the volume and then the mass as well, 272.3 pounds, and then statistics as well. So next one is structural steel. Okay, these are the properties. Okay, just go to the mesh. For now I will just create the default mesh here. So just create the mesh, and then going there, okay, see that one end is fixed, so I would just fix okay, this is the mesh I have created. So go to the statistics, and you see that 12,000 nodes, and there are 625 elements. Okay, you see that I told you how you can identify the nodes. Okay, in the last video I've shown you how you can basically select a particular node, but if you want to know which node is 12,000, then you can also look at that. So for that you need to go to the selection, okay, mesh ID, and then let's suppose I want to identify where is 500 node. Okay, so I would say that 500. Okay, then it would like basically, you see that here is that node. Okay, in this particular area. Okay, so here is the node. Okay, if you can see that maybe it's an internal load, then you can change it to the wireframe. Okay, just change the view. Okay, so this is my you see that 500 node. Okay, that was just for the reference. Okay, and then okay, just leave it. And then next is I have created the mesh. Now I have to apply the fixed boundary condition here. So I using the face selector filter. So just first select the static structure, and then select this face, and then right click, insert, and then okay, fixed board. Okay, so now this face is fixed. Okay, that's fine. And the next one is I have to apply the force here. Okay, which is basically in 3 kilopounds per square feet. Okay, so you see that that's basically, you can say that the force in along z direction. Okay, first of all, and then next thing is our geometry at the top is 2D. So while I have dimensions for one length. Okay, so how I need to convert this Pascal, this is basically pressure per unit length. You see that this is the pressure value, kilopounds per square feet. So while I have, how I can convert that, how I can find that. Okay, you see that first of all you need to determine, okay, how much is that. You see that this is 6.730, so you need to convert that into feet. So basically how much why I'm doing that. Okay, in ANSYS, okay, I can for the 3D geometry I cannot apply the line pressure here as I can do for the line bodies. Okay, there is a pressure option. Okay, so I can apply the pressure here on the face, but you see that this is pound per square inch. Okay, this is not pound per square inch per feet. Okay, so I need to eliminate this dimension. I need to convert this pressure into per unit length. So how I can do that? Okay, I know that this is 3 kilopounds per square inch, and how much is my third dimension? This is 6.730. so I need to convert that into feet. Okay, because that's into feet, so that's why the denominator should also be in feet. So if you solve that, how much value you get? You would get around 5.349. okay, this is kilopounds per square feet. So converting that into pounds per square feet, so that would be 5.349. okay, so I hope you get that. So but this is pounds per square inch. I would change the unit rather than converting that into my value. So just let me convert that into feet. Okay, this is pounds per square feet, and I need to substitute 5.349 here. Okay, so you see that okay, so it would apply distributed pressure on the surface, but you see that this pressure is varying linearly. So that's what I have to do. Okay, the pressure should be 0 at this end, and it should have a maximum value of 5.349 here. Okay, I hope you get that. If you don't, then just remember that whatever the value you get here, okay, you need to divide that by, you see that into the normal dimension. Okay, what are the dimension into the page? Okay, this is the length and this is the width dimension. Okay, so you have to divide that, but keeping in mind the same units. So that's what I have done here. But you see that right now, okay, it will apply uniform pressure, but I don't want to change that. I need to vary it linearly. So just select the tabular option here, and then here, okay, I need the, okay, so you see that in the tabular option, you see that at time 0 the pressure is 0, at time 1 the pressure is 0. I don't want to make it with respect to time. I need the third dimension, which is basically the length. I want to change the pressure with respect to length, so I need to change the time here. So for that, you see that there is a tabular data independent variable time, so I need to change it to the z-axis, which is basically my length in this direction. So just change it here. Okay, so you see that now I have the z. Okay, so it's in written. So at 0, this is the 0. Okay, this is the coordinate. So you see that with respect to my geometry, this is the 0 feet. Okay, and this is the 9 feet. So at 9 feet it's 0, and at 0 feet it has this value. So what was that value? Okay, just for 5349. So at 0 feet 5349, and at 9 feet, okay, this should be 0. Okay, so now it has the maximum pressure at this end. Okay, you see that 5349 pounds, 5349 pounds per square feet, and it has zero pressure here. Okay, which is the minimum value. Okay, now I have this corresponds to this situation. Okay, so now I have applied the boundary condition. Just let's solve the model here. Just right click and solve it, and then just wait a minute. Okay, so we have solved the model and need to determine, okay, the question here is basically to specify the maximum slope and maximum deflection. So I will find the maximum deflection here. So insert deformation and directional deformation, and here I need to change that to y-axis. Right click and evaluate all results. So here you see that the maximum deflection is at this end. Okay, and which is basically the free end. Okay, and it should be maximum here. Okay, as it's shown here. Okay, right now you see that you can see the elements. Okay, I need a smooth, you see that contour. So just go to the results, change it to the no wireframe. So you see that this is really a smooth picture. Okay, so now you see that I have the minus 0.327 feet deflection here. Okay, which is quite low. Okay, so if I go to the solution, okay, here it's in how much, 0.369 inches. So just let me convert that units to inches. Okay, I'm not gonna convert the values. Okay, just change the units here. So inches, you see that this is the maximum deflection is 0.39. okay, this is 10 to the power minus 5, which is almost 0 at this end. Okay, which is basically the fixed end, and this is 0.392. okay, and this is 0.369 or 0.37, which are basically the quite close. Okay, so here you can basically apply the triangular load, and also how you can convert this value into the the pressure per unit length. Okay, so I hope you get that.